All right, today we're going to start Boolean Algebra. We're going to watch multiple times when I stop and pause and kind of have you guys look at it as well. So basically what Boolean by expressions so that we can have a smaller, more simplified logic circuit, and that's going to be easier for us to breadboard. It's easier for us to work with. Just like any kind of algebra problem, the more simplified I can have it, the less likely to work the same way as algebra. In a lot of cases, there are rules, just like there are rules in algebra. Go through those today, and hopefully you guys will kind of see how that works. As you've got B and C, which is this first gate here, or, right, A, that's this one, A, not B, or A, not C. So that can be simplified to A or BC. And since this circuit here looks a lot better than this circuit here, even when I'm breadboarding or I'm trying to put on multisim, both of those, this one, so that's why we want to be able to simplify the best we can. They give you a little bit of history about George from England. He lived in the 19th century, and basically he had all this work about logic and algebra and how the binary system could be used later on in the 20th century. Boolean algebra obviously is named after his idea and who he is. So these are some of our theorems. These are very similar to things that you probably see in regular algebra. So like we all know just x, no matter what the x value is. So these are very similar to that, but it's going to be a little bit different when we talk Boolean because you're thinking about it in terms of ones and zeros. So if I have x and a 0, we know that any time end has a 0 in it, that it can't be true because both of them have to be ones. So x and 0 is equal to 0. X and 1, well, we know again, if anything is anded with a 1, if that value is, it would be a 1. If that value was a 0, it would be a 0. So x and 1 is going to also be equal to just x, because it's just x actually is. If I have x and x, okay, they're the same value. So then my quantity would be 0. If they're ones, then my output would be a 1. The last thing are not x, or not or and not x. So we know like if this is a 1, then this would be a 0. And we know and both of them have to be a 1. So there's no way possible for that to give me a 1. So we know if we have an x and a not x, it's equal to the value of 0. When we're talking about OR functions, if I have x or 0, it's going to be an x because I don't know what the value of x is. It could be a 1. It could be on which one is. It's going to be an x. If it's an x or 1, well, one of them is already a 1. And according to our OR rule, as long as it's a 1, then this would be a 1. So I would go ahead and say 1, no matter what. So I can simplify an x or 1 into a 1. If I have x or x, if they're both 1s, it's going to be an x, or it's going to be a 1. They're both 0s, it would be a 0. So whatever they are, it's going to be an x. If I have an x or not x, and this is the one that gets people sometimes, because if x is a 1, not x is a 0, 1 or 0 is a 1. This one's a 1. So 0 or 1 is equal to 1. The ninth theorem is saying, okay, I can have a double not. So a not x. So basically what it is my and then that not x goes through another inverter. So now I'm not x. So if I'm not x, I'm actually a value of x because it's like a double negative. All right, so basically we're going to learn how to simplify the note that the Boolean theorem used to each step, and we're going to put the answers in sum of products. So again, we want to have our products roll together. All right, so if I'm walking through this, I look here and I say, okay, I have an A and an A. According to my rules, if I have A and A, that's equivalent to A. So this would simplify to A, B, okay? I bring down my OR. If I have a C and not C, according to my rule, that's a 0. So now I have a 0 and D. So they show you that first piece here. Theorem 3 gives me the A where I simplified it. Theorem 4 is where I simplified my C's. And a D. 0 and anything is always a 0. That's according to theorem number 1. B or 0, according to rule number 5, that's still going to be AB. So my final answer would be AB. Okay. Try this on your own. Read through the pieces and pause the video for a minute, and then we'll check your answer. Let's see, okay, I have a B and a B. We know that simplifies to a B. I have a not C and a to A, not C because they're the same thing. I have an B and a 1, that's 1, or to a B, sorry. And I have a not B and a 0, that's going to a 0. What I can also do is, since this whole, I could really just say that this is just not AB. And this is just 0. Because 0 and not B is 0, 0 and A. They're going to walk you through what they did. All right, they brought down their B. They simplified their C. As I said, where we're going to take your, I hadn't got down there yet. You have a B, not C, and they do the same thing. So I can simplify it to one of them. My B and 1 is just a B. So my 0, like I said, it simplifies to a 0. And anything ORed with a 0 is just what that value. My value is B, not C, or not A, B. Okay. Couple other things that are pretty common from just basic algebra. The commutative property or law still exists. Okay, if I have and y, it's the same thing as y and x. Same thing happens if I have x or y. It's the same as y or x. The associative law also occurs. I can take the value of x and have it ANDed with the quantity of y, and that's going to equal the quantity of xy times z. So I can group them differently depending on what will help me simplify the best I can. Same thing's going to happen with my ORs. I can group them here, or I can group them here. It doesn't change anything. Basically looks like the distributive property. So hopefully x and y or x and z is the same thing as the x and, again, distributive property, x and w, x and z, y and w, z, and I OR all of those between them. All right, we're going to simplify. It says simplify the following Boolean expression and note the Boolean theorem used at each step. Put the answer in sum of product. All right, so I have a not RT or, and I've got this quantity here. So the first thing I want to do is distribute piece. So they distributed it. You do r times not r times t, or and t, sorry, not times, not s and not r, and not s t. So then they just rewrote an algebra problem. So then they go and see if there's anything they can simplify. Okay, I have a r that we know is a 0, so I can simplify that, and they use theorem 4 to do that. Okay, so then they rewrote the problem and simplified a little bit. Okay, because they said, okay, anything ORed with a 0, so that's the theorem number 5 that they used, so they just got rid of the 0. On here, so then they looked and we're in good old-fashioned algebra. I have a t in this one, a t in this one, and a t in this third one. So what we'll use that term, the t, that leaves me with a not r, an r, and a not s, not touch this piece. So we're just going to OR that piece and it goes here. Take a second to let that sink in. All right. So then I go and look at what I have here when I factor that out. I have a not r and an r, or an r. One of them has to be a 1, which means that the overall value is a 1. So I put a 1 or not a. And then I know by my rules that if I have a 1 or anything, it's a 1. And now I have or not s, not r. So t and 1 is equal to t, or not s, not r. So I simplified this big giant problem up here to these 3 simple things. So we have a t, r. There's a couple other theorems. These are the ones that are probably the hardest ones, so just keep that kind of in mind. Because a lot of the other ones make sense kind of logically, or they're very similar to the properties you already know from algebra. It's basically what it is. If I have x and a not xy, that's the same as saying that I have an x or just a y. So basically I just drop this not x here. Same thing if I have x and a not x and a not y in the middle. So that's the same as x or not y. The is a not x with the x, y. So that leaves me with a not x with a y. And then again, I have the same thing, but I have a not y. So here if I simplify my Boolean expressions, know that I'm used for each step. So again, I try to look to see if there's anything in common that I can pull out of these to kind of make it a little bit easier to deal with. So the first thing they did is they pulled out the p in these 2 problems here. They did not. The reason they did that is because if I pull out the p, it leaves me with an s or not qs. So that's very similar to what we just saw on the q and my not s are flipped, but that's okay because they mean the same thing. So what I can do is I can now drop my not s, and now I'm going to redistribute my p, redistribute my not q. I look at my first one and my last one. They both have ps in common. So I'm going to pull out, that leaves me with a 1 here, or a q. And the nice thing about that, we know that a 1 or q is a 1. And ps and 1 is equal to ps. And then I can bring down my p, not q. So we've simplified this one. Solutions that you can do. They can be involved with different detailed steps. If you combine steps, basically you can do some different simplifications, and sometimes you'll end up with sometimes you'll end up with the exact same expression. It's just kind of the way you go about it if you simplify it correctly and you follow the right rules. These are all your theorems. You have a sheet with that on them, and so good luck. Make sure you guys help each other. Go ahead and start working on your activity, and have a great day.